Hello class, today we're going to talk about section 10.2, which is simplifying radical expressions. By the end of today's lesson, you'll be able to use the product property to simplify radical expressions, as well as the quotient property, and you will also be able to use conjugates to rationalize denominators. In order to simplify a radical or a square root, there are three rules. First, it does not contain any perfect square factors. So what that means is if you can divide the number by a perfect square, you're going to need to simplify it. A reminder that perfect squares are numbers that you can take the square root of. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225 are the first 15 perfect squares. The square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, etc., etc. So that is 1 through 15, the perfect squares. So it cannot be divisible by any of those numbers. Second, it cannot contain a fraction. So if there's a fraction inside the square root, we're going to have to get rid of that. So the square root is only on the top, or the numerator of the fraction. To follow rule number 3, that there is not a square root in the denominator of the fraction. So we've got two rules to help us out. The product rule is saying that I can take a square root and break it down into its factors. So for example, I can say that the square root of 20 is equal to the square root of 4 times the square root of 5. So I can break it up and factor it just like you would any other number without the square root. Same thing applies with the quotient. So I can say that the square root of the whole thing is equal to the square root of the bottom divided by the square root of top. So for example, the square root of 17 over 3, I can say is equal to the square root of 17 over the square root of 3. So we have the square root of the whole thing, and I can say the square root of the top and the bottom. Another thing that we need to discuss to help us is variable square roots. So when we take the variable square roots, if it is an even number, you can actually take the square root. So the square root of x squared is x. The square root of x to the fourth is x to the second. The square root of x to the sixth would be x to the third. So if you're taking the square root of a variable, you are taking it, if it's even, and splitting it in half. If it is an odd number, we're going to use the product property to help us separate it. So I can split that into the square root of x squared and the square root of x. So it's taking those three x's and splitting them into two pieces. I can then take the square root of the front, so the square root of x squared is x, and then we're going to leave the square root of x by itself because we don't know if we can take the square root of that number or not. Same thing would apply with the next one. I can split it into the square root of x to the fourth, so the closest even number, and the square root of x. Taking the square root of x to the fourth gives me x squared, and I can't take the square root of that x value. Same thing would work if I went up to square root of x to the seventh. I would split it up into that close square root, which is x to the sixth and x, so splitting our 7x's into the two pieces. And then I've got the square root of x to the sixth is x to the third, and the square root of x. So this is how we can break down our variable square roots. So, for example, simplifying the square root, we're going to start with the square root of 180. So I'm going to break that down. I'm looking for things that can divide it that are perfect squares. So in this case, I know that 9 can divide 180, and that's 9 times 20. The square root of 9 is 3, so right now I have 3 square roots of 20. I'm going to go back and look and see if there's anything else on that list of perfect squares that could divide 20. There is, and that's the square root of 4. So the square root of 4 is 2, so now I have 3 times 2 times the square root of 5 for a final answer of 6 times the square root of 5. So that's one way you could break it down. The other way, if you look again at that original number, so the square root of 180, 180 can be divided by 36 and 5. The square root of 36 is 6 square roots of 5. So if you want to make it less steps, you look for the biggest perfect square that can divide that value. Either way, we ended up with the same answer of 6 square roots of 5. Go ahead and try this one on your own. Can break it down into the square root of 9 and square root of 6. Square root of 9 is 3, and we can't simplify the square root of 6. Next one, we have multiplication to start. So I need to simplify this into one square root. Square root of 14 times the square root of 2 gives me the square root of 28. Now I need to check if that can be divided by a perfect square. It can be divided by 4. So I've got square root of 4 and square root of 7, which is going to give me 2 square roots of 7 for my final answer. Go ahead and try this one on your own. Multiplying gives you the square root of 50, which can be broken down into square root of 25 and square root of 2 for a final answer of 5 square roots of 2. Next, we're going to look at something that's got variables involved, and we're going to look at this piece by piece. So first, we're going to look at the number. The square root of 90 can be broken down in the square root of 9 and the square root of 10. X to the third, that's odd, so we're going to break it down into an even square root, which is the square root of x squared, and then the square root of x. Y to the fourth is going to stay as is because it is already an even, so we're going to be able to take its square root. And then that last one, I could split z to the fifth into the square root of z to the fourth and the square root of z. So we split all of those pieces by taking out perfect squares. Now for the final answer, we're going to take the square roots that we can. So we can take the square root of 9, x squared, y to the fourth, and z to the fourth. Square root of 9 is 3. Square root of x squared is x. Square root of y to the fourth is y to the second. Square root of z to the fourth is z to the second. Then we have left over those pieces that we didn't take the square roots of. So we've got the square root of 10x and z. So we took the square roots of the first few pieces that we could, and we left the extras that we couldn't take the square root of inside that square root symbol. Go ahead and try this one on your own. So we broke down all of the pieces that we possibly could, taking the square roots of those pieces that are even. So r squared gives us r, k to the fourth gives us k to the second, and then breaking down those other pieces as we can. Next, we have a fraction to begin with. So we're going to split that up using the quotient property, which is going to give us the square root of 17 over the square root of 9. We can take the square root of 9, so we're going to have square root of 17 up top, over 3. This is an acceptable final answer because there is not a square root in the denominator. It's fine that there's one in the numerator, but we can't have a square root in the denominator. Go ahead and try this one on your own. Bringing it down, you get square root of 21 over 7. Then we're going to go ahead and look at a problem where there would be a square root left over and see how we are going to deal with that. So the first thing I'm going to do is split it up into the square root of 35 over the square root of 15. Now, neither of those can be divided by a perfect square, but we can still simplify it. So I can still break 35 up into 5 and 7, and 15 can be broken up into square root of 5 and square root of 3. Those square roots of 5 cancel each other out, so our problem is currently at square root of 7 over square root of 3. Again, there's still a square root in the bottom, which we don't like. So in order to get rid of the square root in the bottom, you need to multiply both the top and the bottom by that bottom square root. The reason we do this is now after I multiply, I have the square root of 21 over the square root of 9. We can now solve that bottom piece because the square root of 9 is 3. So I end up with the square root of 21 over 3, which again is an acceptable answer because the square root is in the numerator and not in the denominator. So when you are rationalizing, aka getting rid of the square root in the denominator, you're going to want to check to see if there's any common factors, so anything you can cancel out. And then you're going to multiply by the square root of the bottom to make it a perfect square so that you can take the square root. Sometimes there's going to be variables involved. So I got 6y over 12. Again, we start by breaking it up. Square root of the top, square root of the bottom. We then look for common factors. So I can break this up into the square root of 6 and the square root of y over the square root of 6 and the square root of 2. My square roots of 6 cancel each other out. So I've got the square root of y over the square root of 2. It's still not a complete problem because I have a square root in the bottom. So I'm going to multiply by the square root of 2 and the square root of 2, giving me the square root of 2y over the square root of 4. And then we finish by solving, taking the square root of 4, which gives me the square root of 2y over 2. Go ahead and try this one on your own. Canceling out our 8's, which is our common factor, multiplying by square root of 3 on both the top and the bottom, and then taking that square root for a final answer of square root of 3b over 3. If you have questions about this or anything else from the lesson, please let me know when you get to class.